Look up at the night sky, and you are seeing a universe overflowing with variety. We have gas giants, rocky exoplanets, sprawling nebulas, and billions of highly unique stars. All that variety eventually meets the same extreme endpoint. When a massive star burns through its nuclear fuel, its core collapses inward under its own crushing weight, creating a black hole. Here, the universe's complexity is erased. According to a rule in physics known as the no-hair theorem, it doesn't matter if a black hole swallowed a star, a planet, or an entire library. Everything consumed is stripped down to just three numbers: its mass, electric charge, and its spin. Preparing to travel into this dark abyss forces us to ask a difficult question. Where does all that erased information actually go? The first real hint of these objects emerged from Albert Einstein's equations. His theory of general relativity mapped out exactly how massive objects warp the fabric of space. Just months after Einstein published his work, a physicist named Carl Schwarzschild found the first precise solution to those equations. He solved the math while surviving the horrific conditions of the Russian front during World War I, working between barrages of artillery fire. Schwarzschild discovered a mathematical boundary around a hyper-dense mass. If you get close enough to the center, the gravitational pull becomes so strong that the escape velocity, the speed required to break free, surpasses the speed of light. This boundary, the event horizon, serves as an absolute cosmic curtain. It permanently hides the breakdown of physics inside from the rest of the universe. Approaching the event horizon is brutal. You are greeted by an accretion disk, a hurricane of superheated gas spinning violently around a pitch-black center. The mass here is so concentrated that it physically bends the light of the stars directly behind it. This gravitational lensing smears their reflections into bizarre curved loops. To understand what is actually pulling you in, physicists use the river model of gravity. This models gravity as the fabric of space-time itself, flowing inward like a fluid waterfall. As you drift closer to the event horizon, the downward flow of that space-time river accelerates. Right at the boundary, the current surpasses the speed of light. You could fire your engines at maximum thrust straight up, but the space you occupy is falling downward faster than you can travel. Surviving the heat and radiation of the approach only delivers you to a gateway where the laws of physics make returning a physical impossibility. At this exact moment, reality fractures. Your experience of crossing the boundary will completely contradict what someone watching from a safe distance sees. To an observer safely in orbit, time dilation takes over. They see you slow down, freezing at the event horizon. Your image will gradually shift into a deep red color as the immense gravity stretches the wavelengths of your light. Your own watch, however, will tick at a perfectly normal rhythm. You simply drift past the absolute point of no return without feeling a single bump. That peaceful drift doesn't last long inside a smaller black hole. The gravity at your feet becomes drastically stronger than the gravity at your head. This difference in pull stretches your atoms vertically while crushing them horizontally, a lethal process physicists call spaghettification. One observer sees you frozen forever. You experience a rapid, violent descent. Both versions are objectively true, proving that time and space are relative to your position. Plunging toward the very center brings you to the singularity, a single point of infinite density where our known equations simply stop working. Modern theorists describe a rotating ring rather than a solid point. Because stars spin before they collapse, the resulting black hole maintains that spin, stretching the central mass into a rapidly rotating loop. For decades, we assumed this dark center was the end of the story. Then, physicist Stephen Hawking realized a flaw in the math. Despite their immense gravity, black holes are not completely black. Look at this diagram showing the quantum boundary. Here, pairs of particles constantly pop into existence. Sometimes one particle falls into the dark, but its partner shoots away into space. This mechanism, known as Hawking radiation, means the black hole is slowly leaking mass. Over trillions of years, the black hole will shrink and eventually evaporate into nothing. This triggers a crisis in physics. If the black hole vanishes, what happens to the unique data of the stars, planets, and atoms it consumed? This is the information paradox. A foundational rule of quantum mechanics states that information can never be destroyed, yet an evaporating black hole appears to wipe the universe's record clean. The cutting-edge solution to this paradox is the holographic principle. Watch how this is modeled. As a three-dimensional object falls toward the abyss, its physical structure dissolves, but its exact informational blueprint flattens out and is encoded as a two-dimensional grid directly on the event horizon. The complex information of everything that fell inside is stored on the boundary itself. It survives perfectly intact even as the core of the black hole slowly shrinks away. Black holes act as cosmic laboratories, proving that the most profound insights into the blueprint of reality are hidden within the universe's darkest voids. By staring into this abyss, we are finally learning how to read the holographic record of existence.